Hello, BC Calculus students. This is Mr. Johnson, and this is section 3.4, which is on the chain rule. The other thing that we're going to do in this section is talk about our first parametric set, which is a continuation of chapter 1, section 1.7, and we're going to start to do the calculus behind that. So in this section, there is a lot of information. Some of the stuff is stuff that you know from last year, and other things are certainly new. So this is a pretty large and pretty important section. Okay, we're going to start talking about just the definition of a chain rule first. So if we have this composite function f of g of x, then the derivative of this function would be the derivative of f of g of x multiplied by the derivative of g of x. And you've seen the chain rule since last year, and we obviously use it a lot. There's some other notation that is really helpful to understand. We introduced it last year, but let's say that y is a function of u. So in other words, the input of y is u, and u is a function of x. So the input of u is x. Then you could write dy dx as dy du multiplied by du dx. And what you can do with Leibniz notation is rewrite certain derivatives this way, which implies the chain rule, but also is able to sort of separate things out and simplify more quickly. And I'll show you some examples through the notes on that. Okay, we have some derivatives that we need to know. So obviously the derivative of sine is cosine of f of x, and then of course, because of the chain rule, we multiply by the derivative of f of x. Then we have negative sine of x of f of x multiplied by the derivative of f, and secant squared of f of x multiplied by the derivative of f, e to the f of x, one of the most common ones, times the derivative of f, and then a to the f of x multiplied by ln of a multiplied by the derivative of f of x. Okay, so let's try example 1, where we have one of these, common 5 that we've talked about so far in the previous 3 sections. We've talked about trigonometry and exponentials and powers and all that kind of stuff. So in example 1, we're going to talk about e to the power of the square root of x. It may be helpful to rewrite this as e to the x to the 1/2, just because then we can use the power rule. But either way, we get the derivative of e, which is going to be e to the power of the square root of x, and then we take the derivative of x to the 1/2, which is 1/2 x to the negative 1/2, and you could, if you wanted to, rewrite this as e to the power of the square root of x divided by 2 root x. Okay, let's try example 2. So example 2, we have 5 to the power of negative 1 over x, so we're going to use this property of a to the f of x to find the derivative. So the derivative of 5 to a power, some sort of power of x, would equal 5 to that power multiplied by the natural log of that base 5. Remember, we're doing the same thing in the previous problem, but we don't include the ln of e because ln of e is 1. So we're doing the same kind of process here, but e to the x is a unique situation. And then we have to multiply by the derivative of negative 1 over x, which is I'm going to sort of write this over to the side. So this is negative x to the negative first. So if we were to take the derivative, we bring down that negative, so it's positive x, and then we decrease that by 1. So it's x to the negative second there. And then we could certainly rewrite that, but let's not bother right now. Okay, for example 3, it says that f of x is equal to x squared minus 4, and g is a differentiable function of x. What is the derivative of the composite? So if we're, actually what I'm going to do here first is I'm going to rewrite the composite as the quantity g of x squared minus 4. So in other words, I'm just doing that substitution to make it that composite function. So if we were to take the derivative of this now with respect to x, we get the power rule, so 2 times g of x, chain rule, so g prime of x, and the derivative of minus 4 is just 0, and so we get option D. All right, let's move on to the next page. Okay, with this fourth example, we have f of x equal to a e to the negative ax, and we're going to take the derivative, assuming that a is positive here. So we have f prime equal to a e to the negative ax, and then we multiply by the derivative of negative ax, which is just negative a. And you could rewrite this as negative a squared e to the negative ax, and that is option E. Okay, in the fifth example, we have kind of a unique situation where we have basically what I was talking about at the beginning of the section where we were talking about the chain rule and how we can use Leibniz notation to rewrite the form and make it easier for us. What I'm going to do first, though, is I'm going to actually do a substitution. So when we look at u equal to 2x plus 1, I'm going to make this x equal to u minus 1 over 2. And I'm going to substitute this into the equation for y. So in other words, what I'm doing is I'm creating an equation for y in terms of u. I think a lot of people would maybe naturally do it this way, even though you're gonna find it's really cumbersome to do it this way. So what we have here is y equal to u minus 1 over 2 squared, and then those 2's would cancel, so we would get minus u, distribute the negatives, so then plus 1. Now if we were to take the derivative of this, and let's see, I'll just move this up here. So we have dy du, that's exactly what we're looking for, because again, now we have y in terms of u only. So we can do the derivative pretty easy, it's pretty easy to do the derivative at this point. Again, you're going to find that it's cumbersome ultimately because the other method I'll show you will be much easier. So we do the power rule, so we have 2 times this quantity to the first. We have to multiply by the derivative of u minus 1 over 2, which is just 1/2. And then the derivative of minus u is just minus 1. Derivative of 1 is 0. So this happens to be our answer. Now you can see that it's not listed this way at all in the problem. So we need to manipulate this a little bit. Let's simplify. We can cancel the 2's, so we get u minus 1 over 2 minus 1. You can see that still it does not look like any of the answers given, and notice that every answer has an x in it, not a u in it. Now remember that what we have here, I'm going to highlight this, this is x, and that is the equivalent, which means that we have really in this problem, we have x minus 1, and finally that becomes our answer, which is option D. Okay, that's really one way to do this. The other way, and the way that we would like you to start thinking about the chain rule, is that you can take dy du, and you can actually think of it as dy dx multiplied by dx du. So if you were to do that, okay, you have your y equal to x squared minus 2. So dy dx is easy. It's going to be 2x minus 2. We did solve for x to get u minus 1 over 2. So dx du is equal to 1/2. And what we're going to do then is take just the multiplication of these. So again, we're going to calculate this little formula. We're going to take 2x minus 2, and we're going to multiply by 1/2, and we get x minus 1. So I would encourage you, as you start to manipulate your variables a little bit more in our particular class, which is going to be more complicated than AB calculus, utilize the chain rule and the idea of changing around your Leibniz notation in order to change your variable of integration, and sometimes you're going to find that that actually saves you quite a bit of time. All right, let's try example 6. So with example 6, we have all sorts of information. Keep in mind that this piece of the problem is really just chain or composite function. It's u follow v. So we have just u as a function of v, and we're looking for, and we have all this information. We are looking for w prime of 0. So let's first do w prime. That's going to be u prime times v, or of v times v prime, and then we're going to analyze this at 0. So we have u prime of v of 0, which we're told in the problem is 2. And we have v prime of 0, which we're told in the problem is 5. And u prime of 2 is going to be 4. So we have 4 times 5. and so our answer here is 20. So we're just kind of, we're picking through the information they give us. They give us some information that's helpful, some information that's not helpful, and we're just kind of trying to work through and come up with our derivative using the chain rule. Okay, let's move on to the next page. All right, this next page is some of the, I guess, the first information that you have this year, aside from maybe in section 1.7 of chapter 1, where we started talking about parametric curves. This is really some of the newest stuff that you have. So primarily everything we've talked about is review up to this point from last year. And this is really the start of what would be considered some of the new BC material. And this is the derivatives of parametric equations. And the parametric equations we're talking about are the ones that we analyzed in section 1.7, where we had x as a function of t and y as a function of t in order to get this curve in space that is defined by this parameter t that is not really part of the graph itself, but it dictates what x and y are at any point along the curve. So what we're doing is, again, analyzing this idea based on differentiation. So if you have some particle that is moving through space here, like this, we want to still be able to figure out, let's say, the slope or the rate of change right here. Maybe we want to figure out, how much distance is traveled along this section of the parametric curve. We want to find out these types of things because as we look at particle motion and we analyze something moving in space, we want to be able to figure out where it's going and how it's moving and in what direction and when it's stopped and all of those types of things. So we're utilizing our knowledge of AB calculus and the particle motion we did in AB calculus, which was just along either a horizontal or a vertical line. But now what we're doing is we're looking at the motion in space, both in a vertical and a horizontal sense, all put together. So it's much more practical. If you are to take Calculus 3 or multivariable calculus, if you're not a senior, you would be taking that next year. Now what we do is we look at all of this in space. So we take, from AB calculus on just a single line, then we move into BC calculus with a plane, and then we move into 3 dimensions and we look at space. So I think it's a very interesting application behind all of that. So this list of formulas is going to be really important to memorize. So first off, we have the x position of a particular particle is x of t, and the y position of a particular particle is y of t. So x as a function of t and y as a function of t. The velocity vector it has these interesting little brackets here. This is kind of standard. If you look at the IB curriculum, they often use sort of a matrix style bracket where they actually put it vertical. But anyway, with our course and our curriculum, we're using these little bracket things. This is not a set of parentheses because that looks like an ordered pair. This is a vector, and the vector is the direction in terms of x and the direction in terms of y. So if this is your particular vector, then this is v sub x and this is v sub y, and those are considered the components of the vector, and those components tell you in which direction the vector goes. So the vector itself has a direction, it has a magnitude. If you ever watched the movie Despicable Me, you know that character. So anyway, in our case, we really look at the basics of vectors. We do not get into the nitty-gritty. We look at the velocity vector. This is considered the derivative of x of t, so that's dx dt, and this is considered the derivative of y, which is dy dt. And all it is just the two components. So if this number was 3 and this number was 4, that means you go 3 units this way and 4 units up, and that's your vector itself. But again, we're not going to be graphing them. We're not going to be analyzing them by addition or subtraction or scaling them or anything like that. All we're looking at is the velocity vector in terms of the derivative of x and the derivative of y. Now the acceleration vector is really the same type of concept, but it deals with acceleration. So this is going to be the second derivative of x and the second derivative of y. And you can see that over here with respect to t. Okay, so these two are really important, but don't be too nervous. You're not going to really be asked a whole lot beyond just can you find the velocity vector or can you find the acceleration vector. But keep in mind that these values are called components. Okay, so these are the components of each of the vector. Okay, the slope of the tangent line, now remember that's dy dx, but now we have this change of variables because we have a third parameter. So dy dx now becomes dy dt and dx dt. And this is really important for us as we analyze movement both horizontally and vertically. And I'll do some examples with you on that. But remember, when your particle, let's say, in space is moving only horizontally, that means it's not moving vertically. That means that dy dt would be 0 because the particle is moving left and right, but not moving up or down. Now let's say the particle is moving up or down, but not left or right. That means that dx dt would be 0 because there is no motion horizontally, only motion vertically. We also need to know the second derivative. Now this is a little bit more complex because the second derivative is really, I'm going to write this down for you. So the second derivative is really the derivative of the first derivative. However, the challenge here is that it's with respect to x, which means that when we're analyzing a parametric set of equations where t is the third parameter, we really need this derivative to be with respect to t. So what we can do is we can use the chain rule and change our variable of differentiation to be in terms of t as long as we handle the variable on the other side. So in other words, what we're doing is we're changing the dx dt operator, the d over dx operator to be the d over dt operator, and allowing the dt over dx to be accounted based on the chain rule here. Now dy dx in the middle, we're going to write all of this in terms of t. So what we get is d over dt of dy over dt and dx over dt. And then again, we have our dt over dx. And all we're doing then is we're moving this to the denominator just to make it a little bit more, I don't know, straightforward to handle, I guess. And that's where they get their formula. So again, this is one that you need to memorize, but it's not as straightforward as it may seem. I will give you some techniques to sort of help handle this formula because there are some situations where we're able to eliminate a parameter and make life a little easier for us. But that is the second derivative formula. Okay, then we have speed. Remember in AB calculus, speed is the absolute value of velocity. Well, speed is really a calculation of our velocity vector change. And we can get into that a little bit more later, but we have the square root of the dx dt squared plus dy dt squared. Total distance is going to be over a period of time, and really all it is the integration of your speed equation. Now I have mentioned this already, but in this next little part it says a curve has a horizontal tangent. Okay, remember a horizontal tangent means that the slope is 0 when dy dt is 0. And I mentioned that's true because then there's no vertical movement. Now remember that, and I would add this into your notes, that if dy dt is 0, that means there could be a horizontal tangent, but we have to make sure that dx dt is not 0 at that moment. If both of them are 0, then the object is stopped. But if dy dt is 0 and dx dt is not 0, then it's moving horizontally. There's a vertical tangent when dx dt is 0. However, dy dt is not 0, because again, if they're both 0, it's stopped. And that means that you're moving vertically, but not horizontally. Okay? And again, what's happening if we have the 0 in both cases, then the object is not moving either horizontally or vertically. So that's the overview. You have to memorize this stuff. The more you work with it, the better. I can assure you that on, for instance, an FRQ, if you know these definitions, then the FRQ is actually pretty straightforward. And I'll be going over some of that with you as well. Let's take a look at example 7. So with example 7, we're going to find an equation for the line tangent to the parametric curve at the point square root 3, 1. So our first step is to identify the slope. So remember we have the slope dy dx, which is equal to dy dt divided by dx dt. And we don't have either of those equations, so let's go ahead and calculate those. For dy dt, we have 2 cosine t, and then for dx dt, using the chain rule, we have 4 cosine of 2t. So what we're going to do is evaluate this. However, we don't have the t value, because remember, this point that we're given is the point xy. So we have square root 3, 1, which is associated with xy. But again, we need to be able to substitute in the t value. So what this is telling us is that the square root of 3 is equal to x, which is 2 sine of 2t, and 1 is equal to y, which is 2 sine of t. Now we could solve either one of these. We have to make sure that the t value works in both equations. I'm going to choose to solve the second equation because it's just a little easier. 1/2 equal to sine of t, which gives us a t value of pi over 6. And then you can confirm that that works in the other equation. But again, select the equation that's a little easier to solve and then just confirm that it works in both. So back up here to our slope, we're going to evaluate the slope at pi over 6. So in the numerator, we get square root of 3 over 2. And in the denominator, we get 2 times 1/2, which simplifies our slope down to the square root of 3 over 2. So we have the slope of our particular tangent line. We have the y value, which is 1. And we have the x value, which is root 3. So that's going to be our tangent line to this particular parametric curve. Okay, let's move on to the next page and example 8. All right, so in example 8, we're going to look for the moment at which a particle is at rest. So we have x of t and we have y of t, and we're trying to figure out when the particle is at rest, which remember when we were talking about the formulas for the parametric equations, at rest means that both dy dt and dx dt are equal to 0. So that's what we're going to try to find in this particular situation. So let's go ahead and find our derivatives. We have x prime, so the derivative of x, which is dx dt, equal to 3t squared minus 6t. And then we have y prime, that's the same as dy dt, and that's going to be 12 minus 6t. So what we're going to do is solve both of these by setting them equal to 0. So let's start with x prime. We have 0 equal to 3 t times t minus 2, and that gives us t equal to 0 or t equal to 2. And then we can do the same thing for y prime. So we have 0 equal to 12 minus 6t, and that gives us t is equal to 2. So keep in mind, again, we've already talked about this a little bit, when you look at t is equal to 0, that means that dx dt is 0, which means that the particle is not moving to the left or the right. Dy dt is not 0 when t is 0. Therefore, when t is 0, you have a situation where there is a vertical tangent line because the particle is moving vertically because dy dt is not 0, but dx dt is 0, so it's not moving left or right. When t is 2, they both are 0, and that would mean that the particle is at rest. So what we're looking for is when t is 0. However, the answer is in terms of x and y because it's asking for the point xy for which the particle is at rest. So we're going to look at when t is 2, x of 2 is equal to, let's see, 8 minus 12, so negative 4, and y of 2 would be when we have, let's see, 24 minus 12, and so we get 12, which is option A. Okay, let's go ahead and look at example 9. So I had talked to you earlier when we did all the formulas about the way that the second derivative with respect to x is calculated, and that is that you take the derivative with respect to t of dy dx, which again is dy dt, divided by dx dt, and we divide this whole thing by dx dt. So it's a slightly larger formula, and remember the reason for that is that the equations are in terms of t, and yet the derivative is with respect to x. So our first step in calculating this is that we want to find dy dx, which is the same thing as dy dt divided by dx dt, and we get 4t cubed divided by 3t squared, and that simplifies to 4/3 t. So that's going to be dy dx, or in other words, the slope of the tangent line to the parametric curve. The next step is that we're going to take a look at that second derivative. So the second derivative with respect to x would be equal to the derivative with respect to t of 4/3 t, the derivative we just found, divided by dx dt, which was 3t squared. And so here we get 4/3 divided by 3t squared, which is 4 divided by 9t squared. So that is our answer. However, what I want to do is show you another technique that occasionally works and actually can save you a little bit of time, and you don't have to use that really large formula. So this is completely fine. What I've shown you here, this gets your answer. This is the traditional parametric way of finding this answer. There is another method, and that method is to eliminate the parameter t. So in other words, the question is asking us for the second derivative in terms of x. So why not try to take our two equations and put them in terms of x and y rather than x, y, and t. So we start with our x of t equal to t cubed, and we have our y of t equal to t to the fourth. Okay, so let's just say that we have, let's forget the function notation there. We have x equal to t cubed, we have y equal to t to the fourth, and I'm going to solve for t in the equation with x and t. So I have x to the 1/3 power equal to t. What I'm going to do then is take that and substitute it in for t in the equation for y. So what we get then is y equal to the quantity x to the 1/3 power to the fourth, because again I've substituted in for t, which means I really just have x to the 4/3 power. So my equation without the t in it is simply just y equals x to the 4/3. Now if you think about this, this derivative now becomes pretty straightforward. We're going to first calculate dy dx, which is just the power rule, 4/3 x to the 1/3. That's all done. Again, the reason that was so simple is because the derivative was with respect to x, and the equation was in terms of x. So no longer is the t cumbersome. Then we're going to do the second derivative, and that's going to be the power rule yet again. We're going to get 4/3 times 1/3, so 4/9 x to the negative 2/3 power, and that gives us 4 divided by 9 times x to the 2/3. Now, you might say to yourself, okay, are these two the same? Well, they happen to be the same because remember, if x is equal to, I'm going to write this, let's see in blue. So if x is equal to 1/3, or I'm sorry, t is equal to x to the 1/3 power, then what we can do is do a simple substitution here, and we get 4 divided by 9t squared, which again is exactly the same thing as we got before. So if this was a multiple choice problem, for instance, and you had to maybe put your answer in terms of t, let's say you took the approach of eliminating the parameter, which I just showed, then you just have to make sure you go back to terms of t in order to solve, to find the answer, to match the answer. But both techniques in this particular problem work. So I want you to be aware of both techniques. Sometimes one makes more sense than the other. Sometimes one is possible while the other isn't. But hopefully it's helpful to see both techniques here. Okay, that's example 9. I'm actually going to end the video here. Example 10 and 11 will be done through a different video because I do want to show you some calculator work as well. Thank you.